Draw My Neutron Star by Jason and Jaden. This is a neutron star. It is a collapsed core of a giant star. The neutron star has a radius of 18 miles. However, it is very dense because in that 18-mile radius, it contains twice the sun's mass. Inside a neutron star. Inside a neutron star, it contains 4 layers. First, the outer crust. The outer crust contains atomic nuclei and free electrons. Below the outer crust contains the inner crust. The inner crust contains a heavier atomic nuclei, free neutrons, and electrons. Below the inner crust contains the outer core. The outer core contains the quantum liquid where neutrons, protons, and electrons exist. Below the outer core, it contains the inner core. Inside the inner core, there is an unknown ultra-dense matter. Typically, when scientists observe objects in outer space, they usually use a telescope to help create a clearer and closer image of the object. However, in the case of a neutron star, even when using a telescope, scientists still cannot create a closer and clearer image of the star. The way that a neutron star can turn into a black hole is that if it gains more mass. Because a neutron star has such small space packed with a lot of mass, if it gains any more mass, then that neutron star could turn into a black hole. Another way that a neutron star can turn into a black hole is that if 2 neutron stars collided, and then when those 2 neutron stars collide, then that turns into a quark star. And from that quark star, then that quark star will turn into a black hole.
In December of 1933, at a meeting of the American Physical Society, Walter Baade, a German astronomer, and Fritz Zwicky, a Swiss astronomer, proposed the idea of neutron stars. They came to this idea through the question of the origin of supernovas. They explained that the neutron star's release of gravitational binding energy powers supernovas. Neutron stars were first thought out to be undetectable until in 1967, Franco Pacini, an Italian astrophysicist, pointed out that if a neutron star was spinning and had a large magnetic field, the electromagnetic waves emitted could be detected and studied. Little did he know, in the same year, Jocelyn Bell and Anthony Hewish, 2 researchers from Cambridge University, detected the first pulsar, a highly magnetized rotating neutron star. Isolated pulsars produce radiation generally through their rotation as they gradually slow down and cool off. The light is engendered by electrons caught in the pulsar's strong magnetic field, saturated and emitted near the magnetic poles. Considering this, the visible energy is released near the magnetic pole region, though the precise location of the energy is undefined. Binary pulsars are those in orbit with a companion star. Such a pulsar can coalesce matter from the star since their orbits intercept, thus pulling the energy from the star and perhaps other stellar objects. With Hewish as the advisor and Bell as the research assistant, Bell was studying distant radio sources until she discovered a radio signal that was unrecognizable. The source sent out sharp pulses that arrived at exactly 1.33728 seconds. Considering this, Bell and Hewish speculated that the radio signals may not be from neutron stars, but from an extraterrestrial civilization. So they referred to the source of the electromagnetic waves as LGM, or Little Green Men. However, they soon detected 3 other sources of the precisely occurring signals, disproving their initial inference of an outer space species. Thus, they named the source of the radio signals as pulsars, short for pulsating radio sources.